Hello everyone, this is a video about homework 1. This is the announcement video. Um, this is going to be an individual assignment for each of you. We have a heating plant, a third order transfer function for it, and it needs to be controlled, of course. We are going to use a controller to adjust the settling time to be 4 seconds and the overshoot to be 10%. So that's quite important because these are basically the specifications that we use most of the time. And it's also important to note that this is a reference tracking problem. Now here the aim is to kind of track the input. We apply a certain input, we want to see almost the same output so that we are tracking it. This is important. This should be a hint for some questions. Now, when you are designing or when you are answering the questions, you have to give the design steps and equations, and I'm going to talk about that in more detail. Once you completed your design, you will probably have a controller and a closed loop transfer function. And we would like to have the transfer function object representation that's available in MATLAB, and also the ZPK form of that same transfer function, even if it's a controller or if it's the closed loop transfer function. And the reason behind that is most of the time when we have some questions about the design that you've come up with, we would rather look at the zero pole of the transfer function and the controller to double check if something went wrong, if it's correct or not. So TF and ZPK give much detail about your design, so please provide this for the controller and the closed loop whenever necessary. Of course, since this is going to be a reference tracking problem design, and since we are applying step type inputs or step, we would like to see the step response and some step info, what the settling time actually is, what the overshoot actually is about the system, and the pole zero map would also be helpful. So this paragraph here will be aiming almost all the questions here. So when you've designed it, you come back to this paragraph and answer or give the necessary stuff that is requested. So we have Q1, question 1, where we propose a controller, which is an open loop control strategy. And we should regulate the heat as desired. Now here this as desired portion plays an important role because, well, in your lecture notes or in the laboratory itself, we've talked about open loop control. We've touched base on that. Not maybe in depth, but we've talked about it. And there's a certain thing about open loop control that we use, but if you use that on its own, that will not satisfy the 4 seconds and 10% overshoot criteria that we have here. So you have to add something to it to get the 4 seconds and 10% overshoot in the result. So this is not an arbitrary choice. This is basically we expect a specific controller because it is both an open loop control strategy and it should satisfy both the 4 seconds and 10% overshoot requirements or criteria. So you have to maybe think about it a little bit, but you have to combine open loop and then you have to add some stuff to it to get the desired result. And this is a specific answer that we are expecting here. So once you've dealt with that, in Q2 we ask you to use the substitution s equals j omega in order to acquire the stability interval. Now, of course, you can access this data with MATLAB's root locus or rlocus command, or using Ruth Hurwitz, etc. There are many stability analysis tools that you can use and to get the answer here. But this is not quite the question here. We're asking you for a specific method to use, which is the substitution method s equals j omega, in order to acquire the stability interval. So you can maybe verify your results, or you can check if your interval is correct or not by using rlocus or root Hurwitz or whatever. But you should basically answer this question only based on this substitution method that is provided here. And if you think about it, this s equals j omega should resemble you or should give you the hint because it is a specific substitution and we have a system and a controller, of course, in closed loop. So yeah, this should mean something, and it certainly does, and it should give you the idea here. You might want to do some nice graphical stuff where you give the root locus of the system, and once you've come up with the interval, you can just plot maybe those points on the root locus to indicate that these are basically those points, and that everything checks up. Maybe you can create a visual like that, which I probably have done in the laboratory as far as I remember. So yeah, Q1 and Q2 should be obvious. So Q1, open loop controller plus something else, which is a specific answer. Here we have a specific method to analyze the system stability. In Q3 we are looking for a p-type controller design. So essentially you're going to be designing a p-type controller, but here the restriction is the method that you're going to use, because you're not going to use the rlocus MATLAB function directly, where you just click on the graph and then get basically the design. That's not an answer to this question. Even though it gives you the numerical result, that's not an answer, not the proper way of answering this question here. You should basically use the gain and angle conditions that we use when we have pen and paper and a sketch of root locus. So you can see that the whole homework is kind of a classical homework where you have to provide your answers with some explanations and then some design steps and then maybe some verification results. But don't forget to use MATLAB's assistance here, because then life gets too hard. So if you're just having a calculator and a pen and paper, then you're not really good equipped, in my opinion. So for example, for the gain and angle conditions, that these are quite basic definitions that we have. You can just write a script that that uses the poles and zeros of the open loop and the design point, and then comes up with the required vectors, calculates the angle condition if it's on the root locus or not, and then calculates the gain condition. And then you can reuse this. You can basically use the disp command with conjunction with VPA to create some console outputs that we do in the laboratory all day. And those outputs should be actually copied and pasted into Word or LaTeX, and you have to just pay a little bit more attention to it, work on it a little bit, and that should be your resulting report actually. That's how I do it, at least. So, yeah, design a p-type controller using the angle condition and gain condition, not the MATLAB root locus, rlocus function, or whatever. So no ready tools, just the steps and design steps are needed here. Now, once we're done with that, the question 4 is about proposing a controller based on Q3. So maybe there's something wrong about the design, maybe we're not satisfied with the result. So what would we do, or what controller would be a good choice for this, and solely based on the root locus method, of course. Nothing else. The reasoning is based on root locus here. We should propose a controller. The control choice is again not arbitrary. So this is kind of a path from A to B which you should take, and which is specifically designed in this homework. So there's a special path here, and if you obey the rules, you should be good to go. Now you can see that, of course, when you don't use, for example, root locus, if you didn't solve Q3, I would doubt that you would have an idea about Q4. So yeah, that's what it is. Now here we are going to use the gain and angle conditions again. So again, we are designing it from the root locus method, or using the root locus method, and again, not the MATLAB function. Yeah, Q5 is basically a repetition of Q4, but with the algebraic method. So Q4 and Q5 tied together in the sense of that's going to be a controller design. We have a specific controller in our mind. We are going to design them using A, the root locus method, angle and phase conditions, or angle and gain conditions, and B, by using the algebraic method, where we use the polynomial coefficients to equate them to each other to design the controller here. So, and when you're done with your design in Q1, Q3, or Q4 and Q5, you should basically go back to this paragraph and provide the requirements here. For example, TF-ZPK forms, you should apply step to it. So I didn't write it over and over again, but when you have a design, you should verify it, and the verification is basically about step info, step response, pull zero map, and TF and ZPK forms. Now, if you look close to the grading policy here, you can see that we have 90 points actually. They sum up to 90, and then there's a 10-point portion which you get from the quality of report, how clean your report is, how comprehensive it is, etc., etc. And I'm going to talk about it and show you an example ideal report, I guess, so you can see what is expected in terms of the report. Now, let me clarify this again. The homeworks that we have here are basically classical type questions, and we expect you to prepare your answers in a classical manner, as if you would have been in a midterm exam or final exam. But it's not completely that, because you have MATLAB assistance. You have the control system toolbox where you can plug in everything and see if you're correct or not. You can verify your questions on your own, basically. And therefore, it's not that hard as the classical one, but it's also not that easy like a quiz or something where we expect you to provide the code itself, because as you can see, nowhere here in the questions is something like give us the code or provide the code. You will not provide any code because that's not the question at all. You can use some coding and scripting along the way, but that's not the aim here. Therefore, we don't expect you to put some MATLAB screenshots or code screenshots or code copy pastes or handwritten mathematics or text or whatever, because those are not necessary. You're preparing a classical exam type of solution manual to the questions given here. So you should basically use MATLAB's disp function to display stuff, or VPA for variable precision arithmetic, where you have symbolic expressions, where you want to have like this double effect in terms of numerical data to generate your bare minimum of your report. And then you should be basically just tidy it up, give some nice explanations and some graphical results, and that should be it. So it's also not that much from you to be expected, because this is not a book publishing or thesis writing task. So keep that in mind. I will provide you some Word or LaTeX templates which you can use as a starting point. So let me show you the idea report from recent years that I have requested from one of my students, which had a pretty good report prepared, even better than mine, so I wanted to share it with you. Here you can see there's a question, and then there's this body plot, for example, and then there are some steps here where we have some calculations, and you can see there are also these radians per second, these decibels. There are units provided, which is also quite nice in terms of being tidy. And you can see there's K, and then there's this interval, and then there's just at least one sentence about the solution, so not the solution itself, but there's also some wording in it, which is quite nice. And then you have again some stuff here and the conclusion. You can see that the result is basically verified on the body plot itself. We've chosen this point and this point and this point for this and this point for some reason, and that reasoning is behind here. So this is what I mean by verification, by step-by-step explanation. Of course, we don't really need to just have all the necessary steps to it. This is the imaginary part, this is the real part, and then just convert that into this. You can see it immediately jumps to the conclusion. You can use this relation here, and omega is calculated like that. So you can cut corners where you have too much numerical intensity, because that's not necessary at all. And MATLAB should handle it, not we. Then you can see there's some wording, and then again explanation, stuff like that. Everything here is probably copy paste and just update the stuff. And then we have some result here, it repeats here, and then there's a table of all the possible methods that were used, and then all the conclusions here. You can see it's quite good prepared and nicely prepared. You can see that for the algebraic method, for example, these are the set of equations that were solved, and this is basically the solution to it, and then this is the controller, then the verification, again some algebraic method here, and then again another controller, and then they are like shown here. You can see there's a symlink here, and even though here symlink is used and you have the scope here, you can see the scope styling is also updated, which is quite important if you are preparing your homework, because background is probably going to be black if you use symlink scope, and that's not nice at all. If you print out something, that's waste of money basically, or if you use a projector, you will experience that it is not easy to basically project, because the way the projectors work. Now, there are some minor details that mean more than you would expect here, and it goes on like this. You can see there are some matrices involved here, for example, but the MATLAB handles most of the stuff. Here's just the bare minimum and the results, not all the steps, because those are numerical and we don't really care about them. If we have the correct answer, if the result is going to be correct, if the starting point and the algorithm is correct, we don't really bother with all the other stuff here. You can see this is quite a report. This is the ideal case, and this is of course a different homework, so it has too much in it. Your report and homework is not going to be this many pages, and it would not have this many details in it, content in it, because this is homework 1, not this homework here. Now here you can see I have a template here. This is a LaTeX template. I also have the Word template here, which I'm going to upload to Ninova. You will find it in Ninova. And yeah, you can use this as a starting point. Just provide your algorithms, your results here, the step-by-step for the questions that were here. Now, therefore, if you think about it again, we don't expect any MATLAB screenshots, code screenshots, whatever, or handwritten mathematics, because of the fact that you should use MATLAB. In my opinion, you could get away with a MATLAB script that handles question 2, for example, which is a symbolic expression. You have to manipulate symbolic expressions here. MATLAB should help you out for Q2. In Q3, you should come up with a generic script that can basically use the open loop poles and zeros and the desired point, and then create some vectors from those to the design point, and then it should give you basically the angle condition and gain condition immediately as an output. When you have that script prepared, you can just reuse it for Q4 with little modifications, because it's basically the same. You're going to calculate the angle conditions and the gain conditions. And Q5 is basically something that is already given to you or shown to you in the laboratory, because this is the polynomial coefficient method, or the algebraic method, which is extensively studied in the laboratory session. So as you can see, maybe Q1 could be a problem, but everything else can be overcome with scripts, and you should definitely go for scripts, because when you update site stuff, it will update and it will generate some console output. Copy paste that console. I myself do it like that. I just use MATLAB scripts and create the results, and then copy them and then modify them in LaTeX and build a report upon that. So yeah, that's basically it. When you submit it, please create a single PDF file and upload it to Ninova. Nowhere else, no emails, because yeah, it's just becoming too crowded, because this is not the only course that I'm assisting here, and etc. And yeah, just use Ninova. When I use Ninova, I can see the upload time, the date, and everything, and it matters because we have a due date here, and each day that is going to be late, we will basically deduce 10 points. And of course, this is also limited like 3 days at most, because when this homework is going to be online, when the due date comes, homework 2 will be immediately online, and you will be switching from homework 1 to 2, and then from 2 to 3, etc., etc. So we're kind of tied up in terms of the due dates and starting dates of homeworks, and there are not that many weeks in our semester, so it takes quite some time, and we squish in these homeworks here. So don't expect the homework due dates to be extended. even if it's extended, then homework 2 is not extended, and so on and so forth. So I would highly recommend you to attack it as soon as possible, because yeah, timing is important. Well, now I hope that I covered everything. Let me think about it again. Yeah, if you have a question, feel free to ask us over our communication channel, and I would suggest you to ask it publicly to the classroom, because if something went wrong, of course you have to maybe contact us with the answer and reasoning behind it, because I don't know, Q3 is messed up because of this, then you might spoil the answer, then you should contact us privately. But that's not that likely, and other than that, if you're asking a question, you should ask it publicly to the classroom, because maybe someone has the answer and you get to the answer quicker, or maybe someone else or a group of people are asking themselves the same question and you're going to be the voice of them. So it's quite important to ask it publicly to the classroom, to us. And yeah, that's it, I guess, for the explanation here. Because this is the first homework, it took me a while to explain everything in detail. If I missed something, please feel free to ask. Other than that, good luck in your homework, and yeah, see you later.